Welcome to a brand new explainer. Today, we're tackling a foundational pillar of modern statistics, but we're going to do it through a lens you might not expect. We usually think of complex statistical tools being born in these dusty university math departments, right? Surrounded by giant chalkboards and academic journals. But what if I told you that one of the most widely used mathematical tests in the entire world was actually born in a brewery? Yeah, no joke. We're going to demystify the famous T test today, and we're starting with a surprisingly flavorful origin story.
So how exactly did a brewery chemist change modern statistics? Well, to figure out this mystery, we have to transport ourselves all the way back to 1908, to Dublin, Ireland. More specifically, to the bustling, heavily industrial floors of the Guinness Brewery. Now, Guinness was brewing massive amounts of their famous dark stout beer, which was incredibly popular with 19th century porters over in London. But brewing beer at that kind of scale, it's not just an art. It is a meticulous, exact science. Quality controls literally everything. Enter a guy named William Seeley Gossett. He wasn't some math professor, he was a chemist working right there for Guinness. And he was tasked with a very specific, absolutely critical problem. He needed to monitor the quality of that stout beer using relatively small samples of data.
Section 1. The Guinness Beer Origin. A secret statistical brew. Now, Gossett was brilliant, but he ran into a major roadblock. He realized that the existing statistical methods of the time, which relied heavily on massive, large-scale datasets, just didn't work for the practical, small samples of beer ingredients he was actually testing on the brewery floor. So he developed a completely new mathematical approach. But Guinness had a very strict policy. Their brewing methods, and especially their cutting-edge quality control techniques, were highly confidential trade secrets. They definitely did not want their competitors knowing they were using advanced statistics to guarantee a perfect pint. So, Gossett's employer allowed him to publish his groundbreaking findings in the journal Biometrica, but only if he used a pseudonym. He chose the pen name Student, since he was a student of the famous statistician Sir Ronald Fisher. And honestly, that's exactly why, to this very day, it's formally known as Student's T Test.
Section 2. What is a T test? Comparing the means.
So, getting down to brass tacks, the Student's T test is a parametric statistical test used to examine whether the means of two groups are statistically different from each other. Think about it. In research, we are constantly comparing cohorts. Does a special math program make students perform better than the traditional curriculum? Do accountants perform better on a very specific task than non-accountants? In these cases, we have two distinct groups and we have their respective means. The T-test is essentially the mathematical engine that tells us if the variance between those two means represents a real, statistically significant difference, or if it's just a random fluke in our sample data. But here's the catch. You can't just slap a T-test onto any data set you find. When you're dealing with massive amounts of data, say hundreds or thousands of observations, statisticians typically use what's called a Z-test. But remember Gossett's genius. He solved the problem of small samples. The T-test really shines when your sample size is limited, specifically under 30 observations. It's also your go-to tool when the population variance, which is the true spread of the entire group you're studying, is unknown. That just means you have to estimate it strictly from your sample. Plus, as a parametric test, it assumes the data follows a normal, bell-shaped distribution. So when all those conditions line up perfectly, the T-test is absolutely your best tool for evaluating the difference between means. Section 3. Independent versus paired samples. Choosing the right flavor. You're generally going to run into two main variations of this: independent samples and paired samples. If you're comparing two completely separate, entirely unrelated groups, you're going to use an independent samples T-test. For example, comparing the sales figures of store A against store B, or maybe comparing job satisfaction levels between men and women. The groups just do not overlap. On the flip side, the paired samples T-test is what you use when you're looking at the exact same group of subjects twice. Think of it like a classic before and after scenario. You test a group's performance, you put them through a training program, and then you test that identical group again. Because the data points are linked in these matched pairs, the math adjusts to look specifically at the difference within each individual subject.
Section 4. The math behind the magic. Signal versus noise.
Okay, let's break down the independent samples T-test formula without getting lost in the weeds. If you focus on the top part, the numerator, it's just x bar 1 minus x bar 2. That is quite literally just the raw difference between the means of your two groups. Think of that as our signal. It's the core gap we're actually trying to investigate. Now the bottom part, the denominator, involves the variance in sample sizes. This somewhat complex-looking square root is calculating the standard error. That represents the noise, the natural, expected variability or spread in your data. So conceptually, a t-statistic is just the raw difference between your groups divided by the natural variation. If the top number is significantly larger than the bottom number, you get a high t-value, which is a massive indicator that your two groups are genuinely statistically different.
Now, for the paired samples T-test, the math actually simplifies beautifully. Because we are tracking the exact same subjects before and after, we don't have to juggle the means of two completely separate groups anymore. Instead, we just calculate the difference for each individual person, which is represented by D for difference. The numerator, D bar, is just the mean of all those individual differences. And once again, we divide it by the standard error of those differences. It is such an incredibly streamlined way to strip away outside variables and focus purely on whether a specific treatment or a specific training actually caused a real change within those matched subjects.
Section 5. Making sense of significance. Putting data to the test.
Let's ground this in a real scenario. Imagine we're testing the memory capacity of some students before and after a specific training program. Looking at our matched pairs, student 1, for example, scored a 10 before training and then a 12 after training. So their personal difference is -2. Student 3, on the other hand, went from a 9 down to an 8, which gives us a difference of +1. By listing out those before and after scores side by side, we completely isolate that difference column. And this is exactly the data we feed into our paired t-test formula. Ultimately, we want to know, is the mean of all those differences significant enough to prove the training actually worked, or are we just looking at random noise?
To actually answer that, researchers follow a pretty strict hypothesis testing workflow. Step 1. You always start by stating the null hypothesis. In our memory example, the null hypothesis just assumes the training did absolutely nothing, that the true mean difference is simply 0. Step 2. You crunch the numbers from your sample to calculate your t-statistic. Step 3 is figuring out your degrees of freedom, which is typically just your sample size -1. And finally, step 4, you take your calculated t-statistic and you compare it to a critical value that you find in a standard t-distribution table. If your calculated number exceeds that specific table value, boom, you have successfully rejected the null hypothesis. You found a statistically significant difference.
So whether it's brewing a perfect 1908 pint of Guinness or analyzing today's cutting-edge educational training programs, the ultimate power of the t-test remains exactly the same. It takes guesswork completely out of the equation and replaces it with rock-solid mathematical confidence, allowing us to definitively state whether the means of two groups are actually statistically different from each other.
Which really leaves us with this final thought. We live in a world that is increasingly driven by metrics, scores, and endless comparisons. Data is literally everywhere. And your data might have an incredibly fascinating story to tell about a new product, a new policy, or even a new medical treatment. But just gathering the numbers, that's only half the battle. As William Seeley Gossett showed us over a century ago, the real magic happens when you use precise, mathematically rigorous tools to actually listen to what that data is saying. So the next time you see a mean being compared, ask yourself, did they actually put it to the t-test? Thank you so much for joining me for this explainer, and keep questioning the data around you.